Writing code for your Arduino project can be tricky. In this video, I'll walk you through the need-to-know basics. Arduino code is actually C++ code with special functions for interacting with the Arduino. So when you're learning to write Arduino code, you're really learning how to write basic C++ code and use Arduino-specific functions and libraries. I'll point out when we're learning a general C++ concept or Arduino-specific functionality. In this video, we're going to walk through a practical example, connecting a button to the Arduino and reading from it. To do that, we're going to need to understand a few things about the Arduino and a few things about C++ code. We'll walk through these concepts first and then get back to the example. There are three main parts in a basic Arduino program. Two of them are obvious in the template when you first open a new sketch: the setup function and the loop function. The setup function runs once when you first upload your program to the Arduino. Put code you only want to run once in here. It will also run anytime you reset the Arduino, for example, by disconnecting and reconnecting power to the microcontroller. The loop function runs repeatedly after that, forever. Each execution is pretty fast, less than a millisecond, but can slow down if you're running a lot of code. You put code you want to run over and over in here. You've probably noticed that there are a couple lines of code with forward slashes in the default Arduino template. Any line that starts with 2 forward slashes is called a comment and does not contain executable code. A comment is a note to the reader, often yourself, explaining some aspect of the code, like its purpose or structure. There's one more important piece to this puzzle. It's the space outside both functions. This is called the file scope, or global scope. You can create variables here that can be accessed from both the setup and any execution of the loop function. This is important because if you just write a variable inside the loop function, it will be reset each time the loop function restarts. Variables are an essential component of the C++ language. In C++, you define a variable with two parts, a data type and a variable name. A semicolon is also required to terminate the line of code. In C++, a carriage return doesn't signify the end of a line of code. Lines of code are always terminated with semicolons, so be sure to remember them. The angle brackets I use when showing a generic syntax indicate something that will be replaced with a valid piece of code. In this case, data type, in angle brackets, should be replaced with a valid data type, like int. The variable name should be replaced with a valid C++ name, like value. Let's try defining a variable in the Arduino setup function. This variable has type int, short for integer. It can only store integers, like 7, 0, or -3. Now that you've created the variable, you can assign a value to it. Assignment is pretty self-explanatory. You write the name of the variable and set it equal to a value using an equals sign. Let's set our value to 2. It's convenient to combine variable declaration and assignment into a single line of code. Another common primitive data type is the float. Floats can represent non-integer numbers. However, they are only accurate up to 7 digits. Let's create a float in the loop function. Variables aren't limited to storing numbers. They can store all kinds of things. It just depends on the data type. We'll expand on variable types later in the tutorial. Functions are another essential element of C++. You can use functions to encapsulate and reuse several lines of code. Each function has 4 basic parts: a return type, the name of the function, a group of input arguments surrounded by parentheses, and the body of the function, which contains the code that it executes, surrounded by braces. Let's define a function that multiplies 2 integers. We'll return an integer and name the function multiply. There will be 2 inputs, integers a and b. we'll denote the body of the function with braces. Inside, we'll multiply a and b and put them into a new variable c. In order to return the value as the output of the function, we need to use the keyword return. Here, we'll return c. We could also just return a times b without ever creating the variable c, like so. To use a function you've defined, you call it by using its name, along with its input arguments surrounded by parentheses. Calling the multiply function with input arguments 5 and 10 is simple. We can capture the returned value in a variable named product by assigning the result to it. Functions don't have to return a value. Those that don't have a return type of void. They also don't necessarily have inputs. Actually, that's what the setup and loop functions are. They're functions without inputs or outputs. You won't ever call the setup or loop functions yourself, but hidden code added by the Arduino IDE will call the setup function once on the Arduino and then repeatedly call the loop function. Understanding code can be difficult, so it's important to take time to periodically review the contents of your variables. To do that, you need to be able to print the output somewhere you can see it. Because the microcontroller has no screen, you can't use normal C++ commands like cout to print the output. However, Arduino has a simple built-in solution to this problem: serial communication. When the Arduino is connected to your computer via a USB, Universal Serial Bus cable, you can send messages back to your computer from the microcontroller and view those in the serial monitor. To write to the serial port, you need to start up serial communication in the setup function. Call the internal Arduino method by writing serial.begin of 9600 in the setup function. This will start the serial communication with a baud rate of 9600. The baud rate determines how quickly data is transmitted. You can write output using either the serial.print or serial.println commands. You put the variable you want to print inside the parentheses. The println command will print a carriage return after it prints the input contents. Let's use this method to print the value variable. Let's open the serial monitor from the Tools menu and re-upload the code. You can see that the number 2 is printed once because the setup function only executes once. Now, let's define a new global variable called var and set its value to 0. Then, we'll add 1 to it each time the loop function executes using the increment operator ++. Then we'll print it. Here's the output in the serial monitor. var is printed repeatedly, once each time the loop function executes. The value of var indicates how many times the loop function has executed. Another convenient tool is the serial plotter. This allows us to graph values written to the serial port. Let's open it. We can see var starting at 0 and increasing with each execution of the loop function. The heart of Arduino functionality lies in its I/O pins. I/O stands for input-output. There are 3 basic flavors of I/O pin on the Arduino: digital pins, PWM pins, and analog pins. These pin types aren't exclusive. For example, PWM pins are also digital pins. Let's talk about the most basic type, digital I/O pins. We'll discuss PWM and analog pins in the next video. Each digital pin can read or write high or low voltage signals. Depending on your Arduino, the high voltage signal could be 5 volts, for example on an Uno, or 3.3 volts, for example on an Adafruit trinket. In this video, we'll always refer to high as 5 volts, since we're using an Uno. To read from a digital pin, you can use the digital read function. This example reads from pin 2. The resulting integer pin value will contain either 0 or 1. 0 is equivalent to a low reading, and 1 indicates a high reading. Generally speaking, a low reading is 0 volts, but the reality is low will be read for any voltage less than half the high voltage. Similarly, reading high means reading greater than half the high voltage. For example, if the pin is connected to a voltage of 1 volt, we will read low. If we read 3 volts, we're over half the 5 volts, so we'll read high. Besides reading from the digital pin, you will want to set the pin mode in the setup function. If you're planning to read from the pin, set its mode to input, all caps. Writing to a digital pin is very similar to reading from one. For example, to write to a pin, set the pin mode to output in the setup. Then write to the digital pin using a digital write command. The value can be one of two options: low, 0 volts, or high, 5 volts. This example writes 5 volts to pin 7. With those basic Arduino tools in our belt, we're ready to read from a button. We'll start by setting up the circuit. Connect one side of the button to the 5-volt pin on the Arduino. This will be the high side of the button, maintaining a constant 5 volts. 2 pairs of the button leads are internally connected. Each connected pair represents one side of the button. Make sure your next connection is on the opposing side of the button. The opposite side of the button is the switching side. Connect it through a 10 kilo ohm resistor to the Arduino ground pin. The switching side remains at 0 volts until the button is pressed. When that happens, the internal leads in the button connect, bringing the switching side up to 5 volts. The pull-down resistor protects the circuit, safely dissipating the 5 volts. To complete the circuit, connect one of the Arduino digital pins to the switching side. Here I've connected pin 2. We'll use this to read the state of the button. It will be low normally and switch to high when the button is pressed. Now let's write code to read the button state. First, set pin 2 to input mode in the setup function. Then, read the state of pin 2 using the digital read function. We'll save that value in an integer variable called button state. That's enough to read from the button, but we need to verify that we're reading correctly. Let's send the data to the serial port and then review it in the serial monitor. Start up serial communication with a baud rate of 9600 using serial.begin. Now, write button state to the serial port using serial.println. That's it. Upload the code to the Arduino and open the serial monitor. Initially, you should be reading zeros as the digital pin reads low from the switching side of the button. Hold the button down, connecting the internal leads. The values should increase to 1, a high reading. It's easier to understand this data from a plot. Let's open the serial plotter. When the button is depressed, we'll see the graph jump to a value of 1, the high setting. If you're familiar with programming, you might have heard of the DRY principle. It stands for Don't Repeat Yourself. If you adhere to the DRY principle, seeing the pin number 2 hard-coded twice might have caused you to twitch a little. If you ever need to change your pin, you'll have to change it in 2 places instead of 1. That's twice the amount of work. Worse yet, you might change it in 1 place and forget the other. You've created a bug. Adhering to the DRY principle makes your code easier to update and helps you to avoid bugs. One way to improve this code is to define a global integer called button pin and use it in both places. Much better. It's common to see pin numbers and other unchanging values coded using a hash define instead. This preprocessor definition can be used just like the button pin variable in the code. So what's the difference? In order to understand preprocessor directives, we need to talk a little bit about how your code is processed and executed on the Arduino. There are 2 main phases in the life cycle of your code after you hit the upload button. The first is compilation. During this phase, your code is converted from your text input into machine code that can be executed on an Arduino AVR processor. Next, the compiled code is uploaded onto the Arduino and begins executing. The code execution phase is called runtime. Preprocessor directives only affect the compilation phase of a C++ program. Preprocessor directives cannot be changed or otherwise manipulated during runtime the way that a normal C++ variable can. An example is using a hash define. This is formally named a preprocessor macro. If I hash define button pin 2, then, during compilation, all button pin expressions will be replaced with the number 2. I won't be able to change the value while the code is executing, because the variable doesn't exist at runtime. Preprocessor macro names are always written in all caps to help differentiate them from standard C++ variables. Another common preprocessor directive is a hash include. A hash include will take the contents of another C++ header file and place it inside your program. This allows you to use any functions defined in that header. Even though you can't see them, your Arduino program is automatically including headers so that you can access the Arduino functions we've been using so far. We'll be including headers from other libraries later to offer us additional functionality so that we don't have to write it ourselves. I prefer hash defines for my pin numbers because I know they're not going to change during runtime, and the all caps makes them stand out. So far, our program will tell us whether the button is depressed or not, but nothing actually happens when the button is pressed. In this part of the tutorial, we'll make each button press change which of 4 LEDs is activated. To capture the instant when the button is pressed, we'll want to pick up the moment when the button state switches from low to high. An easy way to capture this is to store the previous value of the button state and compare it to the latest value. If the current value is high, but the previous value is low, we're seeing a button press event and we'll execute some additional code. To create this behavior, we'll need to understand conditionally executed code. An if statement is the simplest construct for conditionally executing code. It executes only if a provided condition is true. The if statement has 3 parts: the declaration if, the conditional expression wrapped by parentheses, and the code to be executed if the condition is true, wrapped by braces. To construct a basic conditional expression, you'll typically use a mix of variables and comparison operators. There are 6 comparison operators: equals, denoted by a double equal sign, to differentiate it from variable assignment, which uses one equal sign. Not equal, denoted as exclamation equal sign, no spaces. Greater than and less than, denoted by left or right facing angle brackets. And greater than and equal to and less than or equal to, denoted by an angle bracket followed by an equal sign. To use the comparison operators, you write a variable or a constant expression on both sides of the comparison sign. For example, if I define a value 3, I can compare it to a constant value of 5 in the if condition. In this example, the conditional code will never execute because the value is not greater than 5. What will happen if we change the greater than comparison to not equal? That's right, the conditional code will execute because 3 is not equal to 5. When the comparison expression is evaluated, it actually produces a new value, a bool. A bool is a simple data type that is either true or false. In the last example, the expression value does not equal 5 evaluates as true, and when the if sees a true, it executes the conditional code. For more complex decision-making, logical operators are required. Logical operators combine or change the true-false results of the comparison operators. There are 3 logical operators: and, denoted by 2 ampersands, or, denoted by 2 vertical bars, and not, denoted by an exclamation point. The AND operator combines two bools and evaluates true only if they are both true. Let's look at an example. This example will not be executed because even though val is greater than 3, it is not equal to 5. The OR operator evaluates true if either expression is true. If we use an OR instead of an AND in the example, the expression will be executed because the first condition is true. The NOT operator switches a bool from true to false, or vice versa. If we wrap the first condition in parentheses and apply the NOT operator to it, the expression won't evaluate, because both of the subconditions now evaluate to false. Let's use an if statement to respond to button presses. First, we'll create a global variable for the previous button state. We'll set it to low initially, assuming that the button starts in an unpressed state. Inside the loop function, we're already reading the new button state. Now we'll write an if statement that will execute when the button is pressed. Two conditions need to be met. The previous button state is low, and the new button state is high. Each condition uses the equals comparison operator. We use an AND operator to require that both statements be true. After the if statement body, we need to set the previous button state to the current button state so that it will be updated for the next iteration of the loop. We want to keep track of how many button presses have occurred, so we'll create another global called button press counter. Then, when the button is pressed, we will add 1 to the variable using the increment operator ++. Because we're only going to connect 4 LEDs, we want to reset the button press counter if its value is greater than 4. So let's add another conditional statement. Finally, we'll print the button press counter variable to the serial line. Let's test our code out. You can see that each time the button is pressed, the counter ticks up by 1. When it exceeds a value of 4, it resets to 0. Perfect. Now let's add 4 LEDs to the circuit. The positive side of each LED is connected to a current limiting 220 ohm resistor to protect the Arduino, and a digital pin to activate it. Here, I've connected the LEDs to pins 4, 5, 6, and 7. The negative side of each LED is connected to ground. To turn each LED on in order, we'll use a for loop. For loops are used to repeatedly execute a chunk of code until a condition is met. For loops contain a header with the keyword for and a body of code to execute surrounded by braces. There are 3 parts inside the parentheses of the for loop header: the loop variable declaration and initialization, a conditional statement that determines if the loop should execute, and code that runs at the end of each iteration of the loop. These parts are separated by semicolons. Here's an example. I'll declare and initialize the iteration variable k. We'll start at 0. We'll continue executing until k reaches 5 by setting the conditional statement to k less than 6. Finally, we'll increase k by 1 at the end of each iteration. Inside the loop, we'll multiply k times itself and put the result in a variable called square. With this configuration, the code will execute 6 times. The square variable will be 0 during the first iteration and increase until it reaches 25. There's one more important C++ concept that we need: C++ arrays. Arrays are variables that contain many repeating elements of the same type. A C++ array is declared similarly to a normal variable, but square brackets are added after the name. In some cases, you also need to specify how many elements are in your array. You can use curly braces to compactly assign the initial values of an array. Each initial value is separated by a comma. Here's an example. I'll create an array variable with 5 elements called primes. To access an element of an array, you use square brackets. The index of the element you want to access starts at 0. So, for example, to access the second element in the primes array, you would use primes of 1. In this case, the number variable contains the value 3. The last element I can access is primes of 4. That's the fifth element. If you try to access primes with an index of 5, you're accessing unassigned memory. This results in undefined behavior. Could return some random number, could cause a segmentation fault. Let's return to our button tutorial. Recall that I've connected 4 LEDs to pins 4, 5, 6, and 7. Inside the code, I'll define those pins in a global integer array. I'll set the size of the array using a preprocessor define, n LEDs. Now, I'll write a function called update LEDs. It will turn the LEDs on, one at a time. The function will have 3 inputs: the LED mode, the LED pins in an array, and the number of LED pins. Inside the function, we'll create a loop. The iteration variable k will start at 0 and end at n pins minus 1, which will end up being 3. I'm setting this up so that each time we press the button, one more LED will turn on. So if the LED mode is 0, we want no LEDs on. If LED mode is 2, we want 2 LEDs to be on. To achieve this, I'll write an if statement. If the iteration variable is less than the LED mode, we'll write high to the associated digital pin. We'll determine which pin number to turn on by accessing the kth element of the pins array. We'll also add an else clause to our if statement. The else clause will execute whenever the original if statement does not execute. Inside the else clause, we'll turn off the LED. Let's break this code down by reviewing an example execution of the update LEDs function. Suppose LED mode is 2. Then, we'll start looping through k with k equals 0. When k is 0, it's less than LED mode, which is 2. That means the if statement conditional is true, so its body executes. This writes high to pin 4 because the first element of LED pins is 4. Remember that the first element has an index of 0. Next, the loop iterates, increasing k to 1. Again, the if statement is true because LED mode is 2. This time, we write high to pin 5. Now the loop iterates a third time, increasing k to 2. This time, the value of k is not less than LED mode. This implies that the if statement body will not execute. However, the else statement will execute. This will turn off the LED on pin 6. Pin 7 will also write low. We only need to update the LEDs when a button is pressed. So we'll call the update LEDs function inside the if statement that executes when the button is pressed. We'll pass the button press counter as the first argument to set the LED mode. The second and third arguments will be the LED pins and the number of LED pins. We'll need to reset the button press counter before calling the update LEDs function, so we'll also move that code into the if statement. The last thing we need to do is set the pin modes of the LED pins to output. In the setup function, I'll loop over the LED pins and set their mode. Let's upload the code to the Arduino and test it out. You can see each LED turns on sequentially as the button is pressed. They remain on until the button press counter resets to 0, turning all the LEDs off. Although we didn't see it here, it's common for the Arduino to incorrectly read multiple button presses from a single button press. To correct this, there are methods called debouncing, which ignore accidental duplicate button press reads. While we could code this ourselves, it's much simpler to use an existing library to debounce. Arduino Libraries contain open source code that you can import into your sketch to perform common tasks. You can search for a library online or in the Arduino IDE. The one-button library is a good choice for our application of reading from a button. Let's import it. It's difficult to know which library is best, but you can visit the library's GitHub page to get an idea of how popular it is. While we're here, let's take a look at the examples. These are essential for understanding how to use the library. There are 4 common steps for using a library in your code. First, include the library header using an include statement. The header include allows you to utilize the functions and classes present in the library. Second, create a variable whose type is a class defined by the library. We'll discuss the details of classes in the next video. Third, call any initialization methods in the startup function. Finally, call methods in the loop function as required by your program. Let's update our button read code to use the one-button library following these 4 steps. First, we'll include the one-button header. Then, we'll create an instance of the one-button class. If we read the documentation, the first input argument is the pin associated with the button. We're not using an internal pull-up resistor in our setup, so we'll set the other 2 arguments to false. In the setup function, we'll attach a click and pass it a function called button press response. This function will execute when the button is pressed. We'll write it in a moment. Finally, we'll call the button tick method inside the loop function. The tick method will call our button press response function when the button is pressed. Now, let's add the response function. It won't take any input arguments or return anything. That's required by the interface used by the one-button library. Now, we'll move our code that responds to a button press inside it. We'll increment the button press counter, reset it if necessary, and update the LEDs. The one-button library takes care of tracking the button state for us, so we can remove our if statements and the button state variables. Let's upload the code and test it out. We see the same response as before, but with cleaner code and improved behavior. I hope this tutorial has helped you get started with coding your Arduino projects. Let me know what you're working on in the comments below. Keep an eye out for the next video in this series, which will cover more complex Arduino and C++ concepts, like PWM pins and C++ classes.